Hello, today we are discussing Newton's universal law of gravitation. So, Newton's universal law of gravitation says that a force of attraction exists between any two objects in the universe. Doesn't matter if it's here on Earth, in outer space, some other galaxy, this will always apply. Newton said that this gravitational force is directly proportional to the product of the two masses and inversely proportional to the square of the distance between the two objects. So this translates into the equation F sub g, the force of gravitational attraction, is equal to capital G m1 m2 over r squared. Capital G is the universal gravitational constant. It is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. The m's stand for the masses. M1 is the mass of the first object, M2 is the mass of the second. The main thing here is that it must be expressed in kilograms for this equation to work out. R is the distance between the centers of the two objects and must be expressed in meters. On Earth, because Earth is so large, typically its mass overshadows the mass of any other object that is here, and the radius of the Earth is so large compared to the distance between any object and the Earth that we simplify this to equal weight, or the force of gravity on Earth equals mass times gravity. We should probably put in subscripts of E to say that that is on Earth, and we went on ahead and simplified using those assumptions, and you have learned that g on Earth is a little g, it's the acceleration due to gravity, and it's equal to 9.8 meters per second squared. That is just a version of this universal law with some assumptions being made that we're here on Earth. So today we want to focus on how to use this equation when we are not on Earth, or we're trying to find the force of attraction between objects that are not Earth themselves. So, our sample problem says you are seated 60 centimeters from another student in class. Estimate the magnitude of the gravitational force between you. Assume you each have a mass of 65 kilograms. So, we know the mass of the first student is 65 kilograms, and kilograms is an acceptable unit. The mass of the second student is also 65 kilograms, so we don't need to do any unit conversions there. It does say that you are seated 60 centimeters apart, so that's the radius of the attraction. We cannot use centimeters in our equation, we must use meters. So 1 meter is the equivalent of 100 centimeters. We do our conversion and we get 0.60 meters. Now we are ready to find the force of gravitational attraction. So that's big G m1 m2 over the radius squared. Now we can plug in our values. G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. We multiply by 65 kilograms times another 65 kilograms. And then we divide by the radius in meters, so 0.60 meters, and square it. The number one mistake that I see people make here is you're only squaring the radius, not the entire function. So please be diligent in how you use your parentheses and order of operation on your calculator. When you plug that in, if you have done this properly, you should get a value of 7.8 times 10 to the negative 7th, and your unit label here will be newtons because this is a force. All right, while we are discussing these topics, Johannes Kepler also took a lot of measurements about planetary bodies moving around one another. And there's another pertinent equation that is included in this section of your textbook. It says capital T squared equals the quantity 4 pi squared over big G, big M over times radius cubed. I'm going to box that in because that's an important equation that you could include on your list of equations that we have learned. All right, so what this applies to is this helps you find the orbital period, which is your capital T. We talked about periods earlier in this chapter. And period is the amount of time that it takes for an object to move in a circle around another object. The main thing here is you have to express that in seconds. Your textbook actually says this is an equation used to determine the orbital period of a satellite around a more massive object. I do want to point out and remind you, though, that satellite is not just some man-made hunk of metal technology that we have orbited into outer space to revolve around us. Satellite is a term that technically means any smaller object moving around a larger object. So the moon is a natural satellite of the Earth. The Earth is a natural satellite of the sun. So any smaller body moving around that larger body. So T is the time it would take for that smaller body, the satellite, to complete one full circle. Honestly, though, a lot of times that takes such a long time that it's not convenient to express this in seconds. For example, the moon typically takes about 28 days to orbit the Earth. The Earth takes approximately 365 days or 1 year to orbit the sun. Please be aware that when you're given that information in a problem, like it says that the orbital period is 35 days, you must convert to seconds before you plug into this equation. And you should also know that the equation will give you an answer that is in seconds when you use it. All right, next, the big G is the same big G that we have been using. The M is the mass of the center or larger body. So if we were calculating the orbital period of the moon around the Earth, we would use the mass of the Earth. If we were calculating the orbital period of the Earth around the sun, we would use the mass of the sun. And I would like to tell you that the mass of the sun is equal to 1.99 times 10 to the 30th kilograms, because there are a lot of objects that do orbit the sun, and you might need that as you are working through homework problems. R is the radius of the orbit, or the distance between the two objects, and you must express that in meters, not kilometers, for this to work out, or centimeters, I guess, if it's really small objects. So the main takeaway here is really watch how you are plugging things into your calculator and be super diligent with your units. You must have measurements in units of meters, seconds, and kilograms for all of these laws to work out properly.